Welcome back to Tracing the Sky. So in this video, we're going to pick up where we left off. We're going to continue looking at Mars and how it moves through the sky and some of the things that make it so peculiar. And then we'll start to connect this to the celestial sphere so we can understand what Ptolemy is trying to model and make sense of. So let's hop over to my screen and check it out. Okay, so here we are with another celestial journey. Now, this might look a little bit different than the last video. I've made some tweaks since then because I found some better ways to demonstrate it to you. Now, I would recommend pausing and doing this journey if you haven't already to really get a feel for what's happening here. But I'll walk you through it step by step. So we can see Mars is here rising in the east. Now, over the course of a single day, remember, Mars is going to go from east to west in our arc, right? It's going to move from east to west. But remember, over the course of multiple days, the stars appear to be going around the Earth and then a little bit further. And what makes the planets unique is they're drifting through the stars. And so what becomes really interesting is what happens if we place a dot every position of Mars, let's say every 5 days or so. Can we trace its path through the stars and what kind of path is it making? Remember, we did this exercise with the sun, and the sun was drifting through the stars, but it was always lagging behind, and it was always following the same path. So let's do it with Mars as well and see what happens. Let's move forward 5 days. So I'm going to move forward 5 days, and I'm going to drop one of these markers here. I'm going to move forward another 5 days. I'm going to drop another one of these points. I'll move forward another 5 days. So what you can see is Mars is lagging behind, right? It's always a little bit further behind the stars than it was the previous night. It's not able to catch up to the stars. It's like it's chasing the stars and losing. But it becomes really interesting if you watch this over an extended period of time. So if you haven't done that already, pause the video and click the link to try out the celestial journey, and then come back once you've had a chance, and I'll plot out Mars over many, many weeks for you so you can see how peculiar its motion is. So come back once you've had a chance to do that. Okay, so here we are, and I've moved forward 280 days. What I've done is every 5 days, I've placed a dot where Mars was. And you can see that Mars is lagging behind. But if we examine where Mars is today, you'll see that it's still way further east than when it started relative to the stars. But it does this weird loop-de-loop thing in the middle. Now let's try and make sense of it. And to do that, I'd ask you to ponder a question, and feel free to pause and think about this. Is Mars moving at the same speed? Right, we see it's lagging behind here, but is it lagging behind by the same amount? Or is that changing? Now, what is speed? Well, speed is just distance over time. The distance is the amount it's lagged behind, the length between these 2 points. And the time is 5 days. This is how much Mars has lagged behind in a 5-day period. So one way you could ask that question or consider that question is the gap between each of these points the same? If it's the same, then it's moving at a constant rate. So examine it if you've done this yourself. If not, try it out and think about whether or not Mars is lagging behind by the same amount. Is it moving at a constant speed? And then come back and join me. Well, if you've looked at this closely, you'll see that it is not moving at the same speed. Notice this section here. This is our kind of most important clue to it right over here. What you can see is that Mars is lagging behind, but then the gap between each of these points is getting smaller and smaller. Well, you can think about this lagging behind, that Mars is moving slower than the stars. Well, if the gap is getting smaller, it means it's not lagging behind as much, which means it's starting to speed up. And you can see that around here, Mars is speeding up so much that it starts to move forward again. And it starts to move forward relative to the stars until it starts to pass the midway point of Taurus. But then you notice that gap kind of gets bigger and bigger and bigger, and then smaller and smaller, which means it starts to slow down. And then it gets so much slower that it starts to lag behind again, and it's going to fall behind Taurus. And so Mars is going to follow this really peculiar path. In fact, all of the planets are going to follow this peculiar path. They're going to slow down and lag behind. Then they're going to start speeding up. And then they're going to slow down again. And we call this retrograde motion. this period of speeding up and slowing down, retrograde motion, where we have this little loop-de-loop, right? So this little loop-de-loop is what makes the planetary motion so peculiar. There's really two elements. First of all, what separates the planets from the stars is the fact that they wander among them, right? That they're not, they look like stars, they look like fixed points of light, but they're wandering through the stars. But what makes them particularly different than, let's say, the moon and the sun is that they also have this really wild path where it's speeding up and slowing down. And, you can see here, this loop is not along the same path, but it changes position here, right? It goes a little to the right, right, as it's doing this loop. That's why we call them the wanderers, as they really appear to be wandering around the sky much more than, let's say, the sun or the moon. And so these wanderers make a really particular challenge for modeling. It's really peculiar to model. And let's talk about that next. Well, why is this going to present the Greeks with such a challenge to model? Well, one of the things you have to remember is what the Greeks thought was happening and some of the ideas they held. Remember, they thought the Earth was at the center of the solar system and that everything was orbiting around the Earth in these perfect circles, right? They believed in this idea of uniform circular motion as being the natural way that the celestial bodies moved. And they were really attached to this idea. Now, one thing we can do to understand how they're thinking about it is look at things from an outside perspective. If I click this button here, I can look at things as if we're outside the Earth. This is really cool. So we're standing somewhere in the middle here, and we're facing south. So this is south, and you can see that the zodiac is going from east to west here. And you can see that Mars is wandering among the stars. Now, over the course of a particular night, everything, this entire globe appears to be going from east to west, right? With everything setting in the west. And it's going around the Earth once per day and lagging behind. And what they want to try and do is imagine what would cause all of these things to be moving around us. How could we explain this? And to take it a step further, could we create a model with mathematical precision that would allow us to predict where Mars is going to be over time, right? How things are moving over time. So, how are they going to figure this out? Well, let's remind ourselves of one person, one astronomer, Eudoxus, and how he attempted to model this kind of loop-de-loop behavior of Mars. And that will really set the stage for Ptolemy and the achievement that he's going to make by making his model. So let's have a look at Eudoxus one more time. So here we are looking at things from the outside. You can see that the Earth is at the center here, and we have the stars, and we have Mars. And remember, when we look back at our other journey, Mars is moving through this star sphere, right? Through the star sphere. And we can connect that to what we see on Earth, right? It looked like Mars was tracing this loop-de-loop path through the sky. Now, what Eudoxus did was he tried to explain this using these spheres, and each sphere was at an offset angle. You can see there's this red sphere or ring connected to this green one connected to the blue. And he had each sphere rotating around a central point. So this green sphere was rotating at a constant rate. Notice how it's causing Mars to do this kind of loop-de-loop. Now he's able to check all his boxes here, right? The Earth is at the center. Each sphere is moving in a perfect circle, and each circle is moving at a constant rate. These rings or these spheres are rotating at a constant rate. Now we can play this other blue sphere and see how close he gets to mimicking the motion. Let me turn on our trace path for you, and you can see how it causes Mars to drift further east, but still do its little loop-de-loop, go forward at some points and then back. And he can adjust these spheres to get something more and more accurate. So this is one way that Eudoxus was able to explain the motion, or one way that astronomers were able to explain it. This idea, though, is they're trying to figure out why and how is Mars moving through the stars. Now, what sets Ptolemy apart is he's going to add a level of mathematical precision to his model that's going to make it accurate and hold up to the data for over 1,000 years. So his model is going to be able to accurately predict where Mars is going to be. It's going to be over 1,000 years before anyone can come up with a better model. So in the next video, we'll look at how Ptolemy starts to do this. How is he able to visualize where Mars is and what devices to use that gives him an accurate model? He's going to depart from some of these spheres in order to create a model that's much more accurate. And so that's what we'll pick up next time. We'll start to look at Ptolemy's model and how he's able to get that level of accuracy. I'll see you next time.